Assalamu alaikum. Uh, in this video, the velocity analysis of a 4-bar crank slider linkage with the vector loop method that will be explained using Microsoft Word and the graphical technique according to pencil and scale method and protractor. We must keep ready the complete geometry box in order to physically demonstrate this graphical velocity analysis. So here the statement of the problem is shown. Almost complete data is like that was given in the example 4-3 4-2 in chapter number 4, and here further is mentioned that omega 2 means the input angular velocity to the crank input link. It is minus 30 radian per second. Remember that this minus sign actually denotes that the rotation for the crank is clockwise. So conventionally, if the rotation is clockwise, then minus sign is actually used, and if there is no minus sign, that means the rotation is counterclockwise or positive angular velocity. So we are required to determine the angular velocity of the connecting rod and the linear velocities of point A, which is actually the crank point, moving revolute, and B is actually the slider position. So we will be determining the velocities of the slider and the velocities of the crank point, crank pivot, moving pivot. So we had drawn this diagram for the position on MS Word. Now as the rotation for the crank is clockwise, so that means we can first of all simply represent by for example, we can use some arc just to represent the rotation. Here rotation is in this direction, and we can just create arrow shape just manually in order to just represent here like this. So that means the rotation is actually clockwise, and we can copy further omega 2 here, this notation from another diagram, and we can just paste it here. Here for example we can write that omega 2 is actually equal to minus 30 radian per second. So in this way input velocity is given. So as we can observe that it is actually rotating in the clockwise orientation. So the velocity vector that we can draw here, that will be perpendicular and to this approximately this is perpendicular. We can also create a rectangle just to create the perpendicular symbol here like this. So now our task is to we can mention this velocity VA, we can copy label from here and we can paste, and then we can move the label here, and now we can draw the horizontal reference similarly, or we can copy one reference from here and we can just paste it here for the angle measurement. So now we can measure with the help of protractor the angle between this VA and this horizontal reference. So we can place the protractor here, like this. We will be moving this protractor at this location and here at 0 line, and now we can observe that we can increase the length of this vector. We can first in order to measure the angle, first of all we must confirm that this vector VA is perpendicular. So we first verify or make it exactly perpendicular if we want to measure the angles graphically. And as we can observe that this line is along 120 degree, so this vector must be along 30 degree line, because 120 minus thirty 30 is equal to 90 degrees. So the 90 degree location will be here. Now we can measure the angle. As you can observe, this is the 0 line. Somewhat, if there is some variation, we can move this protractor properly, and here this is 10 degree, 20 degree, and approximately, as we can observe, this is 29 degrees. So this is confirmed because as the angle of the crank with the horizontal is 60 degree, so this angle graphically is 29 degree, and analytically if we proceed this vector in the same orientation of 60 degree, so we observe that this angle is actually 60 degree. So between this vector and this total is 90 degree, so 90 minus 60, so between the angle between this VA and horizontal will be 30 degrees. So graphically it is also showing about 29 degrees, because there are some variations or limitations for the positioning of the protractor. So this is a bit compromise. So the angle value has been verified that the velocity is making 30 degree with the horizontal, and the velocity vector will be located in the quadrant, the fourth quadrant. As we can observe, in order to locate a vector or decide whether a vector is in a specific quadrant, the method is that we will be imaginary placing its tail at the origin, and then we will be observing conventionally that in which quadrant this arrow is located. So as we can observe, this is the first quadrant, this is the second, this is the third, so its arrow is in the fourth quadrant. So in this way we can say that this vector VA is located in the fourth quadrant. So in this way velocity vector VA has been shown. Now we will be first of all, now we must have written the velocity equation. So velocity equation can be written, for example, here, or we can just copy, because from here we can just copy it. We can just copy from there, and you can write it here as we can observe that the velocity of B means our slider is unknown. This is the output. So the equation is almost same. So VA has been defined. Now we will be defining VB relative A. So VB relative A will be perpendicular here. So in this way we can approximately draw it perpendicular in any in both orientations at point B, and we must confirm that it must be 90 degrees. So that can be verified with the help of this protractor. So we can observe here that so in order to for example, we can move this protractor, for example, it's we can say it's 0 line here, and we can move this place this 0 line along this crank like this. Here like this, and now we can observe that this is 90 degree. This is approximately 90 degree. So in this way now we can move this cursor out, and now we can measure the angle between this is the actually the BA line. It can be its correct direction will be confirmed or specified after that velocity triangle has been completed. Before this we cannot actually determine the rotation of the connecting rod exactly. There is technique or method. If we split the motion of the connecting rod into simultaneous translation with the crank point A and then its rotation with about point A, but that concept will be demonstrated or explained later. So at this stage we are not concerned with the exact orientation prior to velocity triangle. So the we just know the line of action of the velocity of VBA. We don't need to specify the exact orientation of the exact direction of the velocity vector for this connecting rod at this instant. So we can copy this label and we can paste this label here and we can change it to as VBA and like this. So this is the velocity VBA line and its angle with the horizontal that can be measured here. We can again set the protractor in the principal orientation 0 degree along x-axis, Now we will be placing it here and now we try to observe here approximately that this angle, if we this is for example 180 degree and this is 190, this is 10, 20, 30, 40, 60, 70 and we can say 75, 76. So approximately this VBA along the horizontal is 76 degrees. So that can also be verified that from the fact that 90 minus 26. So as we can observe here, we can type 90 minus 26 degrees. So this is 64. So our observation, we again verify that if we have made mistake in inspection, so here we can observe that this is 10, 20, 30, 40, 50, 60, sorry, this is actually 65 degrees. So here it is mentioned 64, so our result is quite similar and very nearly equal. So we can mention the angle here. We can just copy this symbol and we can repaste here and we can similarly move and further resize it, that actually this angle is actually our requirement and this angle is this angle is 64 degrees almost. So the angle of VBA with the horizontal, that has been also shown, and now remains the third vector VBA, and if the crank is moving in this orientation clockwise, then necessarily the slider will be moving towards right, so and that will be horizontal. So we can simply denote here a simple arrow and we can copy this label and we can paste and change it to VB, just like this. So in this way, this is the location the VB. So now we know the orientation or direction of the rotation and direction of translation of the slider B, and now we will be drawing the velocity diagram. So velocity diagram can be drawn on the next page. Sorry, like this we can move on to next page. Here we will first of all be specifying the scale for the velocity. Velocity scale for graphical work. So here, as we observe that the magnitude of the VA, as we can say, the magnitude of the VA in velocity of point A is equal to O to A, O subscript to A, sorry, and this must be the subscript, and so O to A. Sorry, O to A, this is the velocity VA, and into omega 2, that can be copied from here. Multiplied by omega 2, and this will be equal to, as we can observe that O2 is 40 millimeter multiplied by omega 2, which is equal to 30. So this comes out to be 1200 millimeter per second. So the scale that can be suggested is that, for example, I can say that 300 millimeter per second is equal to 1 centimeter or 1 inch, for example. So according to this scale, we will be drawing first of all the velocity VA, and the orientation of the velocity VA is known. So its magnitude and velocity both are completely known. So now we can first of all satisfy its orientation like this. Direction, we will we can first of all draw the horizontal reference, or we can copy from here at any suitable location. We can copy and we can paste, so that the protractor zero line or horizontal line, 0 and 180 degree line, is actually coinciding or overlapping this line. So like this we will be placing the protractor here, and now we will be confirming that this angle that must be, this is 60 degree, theta 2 is actually 60 degrees, that theta 2 that can also be mentioned here. For example, we can copy this label and we can paste it there and change it like this. We can, for example, we can set theta 2 and this label to be 60 degrees. So we can this label to be 60 degrees like this. So theta 2 here, that can be simply mentioned, this is 60 degree, so this is actually 30 degree. So we can just copy this label from here, from here, and we can paste it there. And we can change it to 30 degrees, and we can move this V out of this location, this VA at where the velocity VA vector, and here we can move it here, and again we can use the arc symbol simply from here, and so that angle is mentioned here like this. We can a bit rotate it, and then we can move it here like this. In this way we can further resize it. Here like this. So this has been mentioned, this angle must be up to this vector line here like this. So theta 2 has been mentioned. So this 30 degree has been mentioned, and now we will be measuring its length according to scale, which will be equal to 1200 divided by the scale, and scale has been selected as to be 300 millimeter to be 1 centimeter. So this is equal to 4 centimeter for better clarity. So now we can move this scale to measure 4 centimeter, and we will be placing it parallel to this vector. Actually like this. So as we can observe, this be 4 length. So in this way this vector has been placed. So now now we will be moving this protractor and scale out from this location to draw other vectors. So VA has been drawn and that can be labeled. Remember, another technique is there that this VA can also be transferred from at the same angle, because once this angle has been specified on this positioning diagram, so we can just for example copy this vector and just we can paste it here, for example, and then we can be just moving it from the middle. So as we can observe that this is actually the exact location. So due to the placement some incapabilities, so there is a slight variation, a slight mismatching. So this is the vectors can be moved or placed like this as well. However, VA has been defined and at 30-degree angle. So now we will be drawing vector VBA line. So we can again be copying this reference from here and then we will be placing it here, and now we will be now vector VBA line will be placed. So we can for example draw this line here, perpendicular, at the given angle as it is given there, and we will be proceed extending it in both orientations, in the upward and downward, and this angle must be equal to this angle of 64 degrees, this angle between this horizontal slider axis and this VBA line, so 64 degrees. So we can now confirm. We will first of all be moving this protractor and placing it here like this, and now we can observe that this is 10, 20, 30, 40, and this line must be along 60-degree line. So here we can observe that first of all we will be placing this line here, so that angle is actually defined. So this is 10, 20, 30, 40, 50 or 60. So this is actually at 120 it is 60 degree, so here it is actually 64 degrees. So as we can observe here, 10, 20, 30, 40, 10, 20, 30, 40, 50, 60, and this is 64 approximately. So now we will be extending this line, moving from the center point like this. So at this, so we can move this cursor away, this protector away. So as we can observe, we have drawn this VBA line. Now our last line actually last vector is VB, and VB vector is actually the resultant. So the resultant vector VB, that will be actually be starting from the tail of this vector VA, and that will be connected with the head of this vector VBA, because VB is the resultant. So we can simply draw, and we also know its correct orientation. So here like this. So the intersection is at this location. Actually we don't require to exactly know the direction of motion of the slider. We actually just know that the orientation of movement of the slider is along horizontal. So actually we can, instead of arrow line, we can just draw a simple line, and we make actually the intersection here, intersection at this location. And now the intersection is there. Now we will be satisfying the arrow signs and this velocity equation which is shown here, and that actually equation states that the VBA vector will be vectorially added into vector VA. So the tail of vector VBA will be connected with the head of vector VA, and the tail of the velocity vector VB will be starting from the tail of velocity vector VA, and that will be connected with the head of velocity vector VBA. So because VB is actually the resultant, so in this manner we can complete these vectors like this, and here like this. And now we can observe that now we measure the length of these vectors to determine the magnitudes. So bring this scale and measure their lengths. For example, first of all, for example, we can measure the length of the slider approximately very carefully, and as we can observe that here the length of the slider, we can further zoom in for better view. As we can observe here, this is actually 4.2, for example 4.2 centimeter. So according to scale we will be converting 4.2, and we will be multiplying it with 300, because according to scale 300 millimeter per second was equal to 1 centimeter. So this is 4 centimeters, so the value comes out to be 1260 millimeter per second. So slider velocity, here we can write that VB, that will be equal to VB equal to 1260 millimeter per second, as it has been calculated here. Remember, never forget to mention the units while in exam, because units are very important. Here like this, VB is 1260 millimeter per second. according to scale. So here we observe that the value he has mentioned here for this is 1346. So our results are quite near and matching. Our results shows 1260 and here it is mentioned 1346. This is the magnitude for the open circuit. So we can again verify for the graphical work, because analytical results give 100% accurate results, ideal results. So we must again verify the exact value here like this. As we can observe here the value actually of just one mark or one calibration difference make a lot of difference in the analytical results when we will be observing or inspecting these measurements graphically. So even one mark may create great variations. So we must always draw precise diagram as far as possible. So here now as we carefully observe that is 4.2 4.3. so if for example we can assume for example here by observation by inspection that it is 4.4 for example, instead of 4.2 we can take it 4.4 centimeter the length of the vector, then multiply it with the scale, and as we can observe this is 1320. So even 2 mark difference is making a great difference and our results are approaching the analytical results. So in this way there are 10 to 15% variations in the graphical results as compared to the analytical results are allowed. So no issue, our diagram is quite okay. So in this way VB magnitude has been found out. So the latest value that has been shown here, that is 1320 for example. So the my purpose is just to explain the methodology. Now we can measure the length of this velocity vector VBA. So we can move at parallel to this, and from any location at any point we can for example we can start from here, from the 7 mark. So 1 centimeter, 2 centimeter, 2.1 2 3 4 5, and for example it 2.6 I can observe that it is 2.6. so 2.6 multiplied by 300, so this comes out to be 780. And if we verify the results from analytically, as we observe that it is here, as we consider VBA magnitude, it has mentioned 673.92, means for example 674, and our results are 780. So this is also due to just a difference of 1 mark. For example if here it were 2.5 for example, we can if we would multiply with 2.5 multiplied by 300. As we can observe, it comes out to be 750. So in the graphical analysis, these 1 or 2 marks make a great difference. So we must carefully measure the length of the vectors. So here, as we can observe, this is 2 centimeter and 2.6 centimeter, for example. So in this manner we must be very careful while calculating. Now we can calculate their magnitudes. So remember, the magnitudes will be we will be dividing velocity vector VBA. We can label it here. This is the velocity vector VBA here, and this is the velocity vector VB, for example, as mentioned. This is the velocity vector VB. So now the angles can be angles are quite clear of the velocities, as they have already known, and the internal angle for these triangles can be now graphically verified. And as we can observe, the angle between VA and VB was 30 degree, so we can mention this angle. We can copy just, and we can just paste it here. So this angle is 30 degree. This is actually the angle of the velocity VA2. So this is not actually theta 2, but it is this angle is 30 degree. And as we observe that VBA, it had its angle was along the horizontal was 64. That means this angle is also 64 degrees. So we can simply copy this, and then we can just change it here to be 64, and we can put it here, because this angle 64 and this angle between this VBA line and this horizontal, these are actually alternate angles, and these are quite equal. So these are all 64. So I can mention here just for clarity. This was also 64 here. So this was also 64. So these are alternate angles. So this third angle now can be obtained by subtracting the sum of this angle 30 and this angle 64 from 180 degrees, because the sum of the angles in a triangle is equal to 180 degrees. So as we can calculate here that 64 plus 30, and for example we will be minusing it from 180 degrees, so this comes out to be 86. So this angle can be mentioned here to be 80 degrees. Like this. So in this way, now this triangle has been graphically solved. You can solve this triangle by the law of sines, because all angles are given and one side length is completely known, this VA. So this can be solved trigonometrically using a law of sines and cosine, and the results can be verified graphically in this way. So do it yourself, and if you have any question, personally meet and ask for any clarification. Thank you and Assalamu alaikum.